안녕하세요. 저는 크립토서울의 강현정 대표입니다. 이렇게 월요일 날씨가 정말 최악의 날씨임에도 불구하고 이렇게 와주셔서 너무 감사드리고요. 사실 이 미덥은 5일 전에 제가 연락을 받았었어요. 그래서 카데나 팀이 한국에 온다고 연락을 받았는데 사실 저는 익히 들어온 정말 유명한 팀이어서 꼭 이제 시간이 부족함에도 하고 싶었어요. 그래서 이 팀을 실제로 만나보고 싶었고, 그래서 워낙 유명한 팀이어서 좀 배경도 되게 궁금하고 어떻게 설계하게 됐는지도 궁금해서 초대하게 됐습니다. 그래서 급히 이렇게 공지를 올렸음에도 불구하고 와주셔서 너무 감사드립니다. 크립토서울은 잘 모르신 분들을 위해서 설명을 좀 드리자면 저희는 한국에서 커뮤니티 빌딩을 도와주는 팀이고요. 이제 해외 프로젝트 중에서 좀 기술적으로 많이 활발한 활동을 하고 있는 팀들을 한국에서 더 좋은 활동할 수 있도록 도와주는 그런 이제 팀이고요. 저희는 지금까지 한 10회 정도의 공식 미더블 해왔습니다. 그래서 올해 4월에 출범을 만들어졌고요. 그래서 앞으로도 더 왕성한 활동을 할 예정이니 많이 추천도 부탁드리고 좋은 프로젝트 있으면 많이 좀 추천도 해주세요. 그래서 좀 최대한 많이 활동을 하도록 노력하겠습니다. 자, 그러면은 저희 엄청난 좋은 비주얼이 있는데요. 저희 멀리 뉴욕에서 온 팀이고요. 그래서 카데나 팀을 좀 박수를 부탁드리겠습니다.
Thank you. I don't know what you said. I don't know what you said, but thank you. So I'm Will Martino, co-founder of Kadena, and this is Marie Leaf, our head of product.
Hello.
Marie, do you want to either move over there or come next to me? So we are Kadena, and what we're here to do is to fuel the incredible burst of business and societal transformation with technology that lets us actually achieve the true value, really the true potential of what blockchain is. It's the reason that we're all here. It's the ethos of the community. Before we dive into it, this community has been around for about a decade now, or the space has been around for a decade. I'm curious to see, by a show of hands, how many of you own any cryptocurrency? Cool. Thank you.
Okay, so a good ratio. Out of that, how many people have developed decentralized applications using smart contracts on possibly the Ethereum blockchain or other blockchains? Okay. So we have a couple of developers in the audience. And out of curiosity, how was that process? Was it easy? Not easy. All right. Well, you've shown up to the right presentation then.
You have one more? No? All right. So, by touch of background, my co-founder, Stuart Popejoy, currently in New York, him and I met at JP Morgan. If you've heard of the project called Juno or Scalable BFT, I was the lead engineer for those. My co-founder was the head of the desk before Quorum, which is the enterprise Ethereum project that JP Morgan released. There was Juno, which was this from-scratch, high-performance private blockchain. And we met there and put this together. If you're familiar with Icon, if you look at their older consensus protocol white papers, you'll actually see Tangaroa, which was a Stanford research project, Scalable BFT, and Juno, which are Kadena's or my projects, actually discussed kind of in detail inside of the papers. So what we're building, and this is really about who we are to frame the discussion before we get to Chainweb. We provide a secure and scalable platform, and through that we use proof of work. We use braided chains, which is going to be Chainweb, which we're going to discuss. In addition to that, we have a smart contract language called Pact, which runs on several consensus protocols. One of them is our private blockchain, and then Chainweb is our public protocol, which we'll get into. The key is that we reimagined everything except for proof of work and for cryptography from scratch to build a system that we knew you would need to really service the sophistication that an enterprise project would represent. So something as complicated as a global supply chain. And then we built that tech, and now we're bringing it to the public. We're democratizing that very high standard of engineering. And this is both through Pact and how our protocol and how our consensus protocol works.
And just to add to that, the other founder who's not here today, Stuart Popejoy, he built Pact, and he is the same person who built the language that traders at JP Morgan, who are not technical, who are not developers, use in production every day to execute trades, so real world trades. So he's taken the same sort of design principles of making it very secure and very not generalizable to any function you can imagine, but only specific to blockchain functions. And that is how we get around the issues of like recursive call attacks and or you were gonna speak more about Pact.
Sorry. It's a good background for it. So this is some very simple demo code for Pact, and Marie was entirely accurate on her description of the design principles for it. It's designed, it's a domain-specific language for blockchain. So that means that there are certain things that are difficult to do, and those are intentionally made difficult because by making them easy, they would also open you up for bugs. So AI or just pathfinding, that type of thing doesn't belong on a blockchain at the protocol level. It should be off-chain and then results brought in. So, but things like, blockchains are fundamentally about transactions. So for the people who know Solidity, I usually start the sales pitch with, I don't think we have an example of an error here, but we have actual error messages, which is a big deal if you're from Solidity. You don't have the problem of just out of gas in production, and that's your error message. We also have, and this is what we define by upgradable, that is how you upgrade both this code and the data that it protects. Pact is an interpreted language, so that means that this code is what gets stored on the ledger, is what gets run. The computer and you are looking at the same thing when it is executing. And there's a lot that goes into this, and a lot of stuff that both feels very natural and is very unnatural for a blockchain, just because the way that Solidity was designed has led to some obvious problems. The icon, I think it was IXC bug, where it was a not equal versus a double equal. We have formal verification for taking care of that kind of thing, those more unavoidable aspects. This is Chainweb, which we're going to get into in a second in more detail, and there's the graphic that was up before, so I'll skip over this for now. We were founded in 2016, and we came out of JP Morgan, as I mentioned. We plan on launching the public chain in Q1, probably March of 2019. We've been working on it for about a year. We'll get into who are our backers, who knows about us in the States in the next slide. And we'll get into also kind of this longer term roadmap and how Chainweb gets involved, because Chainweb, unlike I think possibly any protocol that I've run into at least, has this path for increasing the throughput as adoption increases. You can go from smaller to larger networks without degrading the security of the system itself. Kadena has been live in the enterprise sector for about a year. This is a Fortune 100 healthcare client. Forget that when I go abroad, we have to describe that the healthcare system in the United States is very broken, and they're very big companies that make a lot of money trying to fix it. One of those companies we've been working with for about a year. They now have a consortium of several others that they're coming together to do a incentivized data marketplace. So this is a very, it's an easy to understand problem in that These companies need a certain data set. If they build their own teams to go and get it, they can't actually make it correct. It's always wrong, and it's wrong enough that it costs them a bunch of money. They can't go to a third party who has a team that's dedicated to making it for the exact same reasons. The data set is just very hard to get valid, and it doesn't provide any upside or any, how to describe it, any benefits or advantage to the person who has the best data set. So it's not a competitive thing.
So to give you a more concrete example, it is a database of patient service providers, so doctors, anyone who's providing medical services, and in some cases they have the doctor's home number or the doctor's cell phone number, and they get calls at like 2 a.m., 3 a.m. in the night. It's just a big, when I use the word cluster,
It's a mess.
it's a big mess of data that no one person is incentivized to clean up alone, but because now they have market dynamics, they can incentivize each other into providing the best clean data.
Thank you. Clicker doesn't work. So, on to Chainweb. The first thing to kind of make clear is where this sits in the stack. The way that our platform works is that we have Pact, which sits at the, that's really difficult to do from this angle, which is a interpreted smart contract language. Think of it like SQL almost. And then it runs off of multiple different consensus protocols. Right now it runs off of Scalable BFT, our enterprise consensus protocol. Next year it'll be running off of Chainweb. That'll be when we launch the public network. I also expect to be putting it onto other protocols once we launch. Right now the strategy is to launch the public and then to start integrating it with Tendermint and with probably EOS. I wouldn't be surprised if Hyperledger also got an integration. The smart contract language itself is designed to be swappable on top of the consensus protocol. I don't think that there's going to be one protocol, so one type of cryptocurrency that rules them all. I'm more of a believer there's going to be multiple ones, but I do think there's going to be standardization around smart contracts because they're a very mission-critical piece of software, and we really should be devoting our resources to a path that has a very clear roadmap to getting to where we're going to need to be, and that's something that's safe enough to, that's on the scale of really mission-critical stuff like aircraft control systems. So,
just out of curiosity, to ping the crowd again, who here has worked with SQL before and done any SQL querying? All right, so we have a couple people. Who has worked with Excel and macros in Excel? Okay, a couple more people.
yeah.
Well, we have an Excel Pact integration that Will can speak about.
Yeah, so we don't plan to just address the market as it exists now. We just plan to expand the market quite dramatically. And the way that we plan to do that is to go and have a larger user base of people who can program in these languages. So Pact is designed for a non-programmer, someone who's technical and knows the domain, but doesn't actually code, because for a number of reasons, but the main one being that at a large scale, you need to actually have lawyers and executives reviewing contracts to make sure that the business flow is right. And if you're going to have that at the end game, you need to have it up front because you can't take something and then move it there over time. You need to have that baked into the core DNA. And by doing that, it also opens up Excel programmers and the marketers who learn SQL and a bunch of other people, like type of person or career that aren't programmers but still code. They just don't code professionally, and opens it up for them to come on and be a participant in the community. So Chainweb is the rest of this talk. Now, the core of it, just proof of work, 101 basics. This is what Bitcoin, so Nakamoto consensus as it's called, first put out about a decade ago, back in I think it was 2008. And this is just where miners are assembling new transactions and then brute forcing, we're just racing to get a certain solution to the math problem that those things represent. And then it also has a way of figuring out which fork, if there's ever a fork in the network, is the one that you pick. So it's just the longest chain wins. So, simple example of what it looks like. You have a block, let's say this is the new one. When it's generated, it points to the previous one. If there's a fork, which of these two forks would then race, and then one would get picked. And this is Bitcoin. Ethereum has these things called uncles that are sort of down here. And there are other blocks that were mined that don't get included, and it's just kind of their header. That allows Ethereum to have a much faster confirmation time than in Bitcoin's, which is closer to an hour. And that's what we've been looking at when it comes to proof of work for about a decade now. And some alternatives were, let's get into this for a second. So the core of Chainweb is that we're going to take that idea, that traditional single chain blockchain, and have multiple ones that are parallel, and then have them also referencing each other. So you're going to be braiding these things. So you can think of it like, let's say you have a hose and you have water flowing through it at, I don't know, a liter a minute or something. And one way to increase the overall capacity of that system is to say, okay, instead of having one hose, we're going to have 10, and we're going to braid them into being just a bigger hose. Now, these are still individuals going at a liter a minute, but now we're going at 10 liters a minute. It's kind of the idea. The other intuition is that by braiding them together, if you want to go and change something somewhere in that big braid, you need to unbraid it, change it, and then rebraid it. So that adds complexity, it adds work, which in this style of consensus adds security, which actually then decreases your latency, your confirmation time.
So the global hash rate of the entire network stays the same, but as it grows, the difficulty per chain decreases, but you retain the same security because now all the chains are referencing each other.
Yeah. So this was a structure initially proposed by Blockstream, or I think it was about 4 or 5 years ago, called Betacoin or Block Rope, and it was just this would be Bitcoin as it exists today, and then this would be the beta version of Bitcoin for upgrades, and they'd be running in parallel, and miners would be working on both. The next block for here and the next block for here. And when this block is, and so when you're making this block, you need to not only reference your previous one, but that of your peer. And this was proposed primarily for security reasons, because as you increase the number of chains, while keeping the hash rate the same, you end up sampling from this hash pool, the thing that's doing the consensus, more often. And the more often you can sample from something like that, the faster you approach the real world value. And the faster you approach the real world value, the tighter the bounds on your security you have. This is all assuming that you don't have someone with a majority of the network. And the faster you can approach something, where you need, the only way to subvert it would be to actually have 51%. The faster you can do that, the better security you have. So this wasn't followed up on, and they actually went in a different route, but there is some historical context. It's not a totally new idea. The real innovation of Kadena is the addition of graph theory down here. So instead of having every chain every block be referenced by every other future block, there's only a subset that reference it. So these graphs are all degree diameter graphs. Degree diameter graphs are just a very famous graph theory problem. And you want to say how big of a graph can you make for a given degree and a given diameter. So the diameter for this is it's a degree 3, diameter 3 graph, which roughly translates to when a block is made, it's referenced by, for future blocks, it's referenced by its future block and 3 of its peers, so that's the degree 3. And then after 3 steps, so when it's 3 blocks deep, it's referenced by indirectly and then directly the rest of the network. And this structure drastically increases the security while also increasing the overall throughput of the system. because in a proof of work system, you always have to wait a certain depth to hit confirmation time. And the trick that Kadena pulls with Chainweb is that while you're doing that, while you're waiting for confirmation by getting a sufficient depth, you're also getting extra throughput from these other transaction streams, these other chains that are in the same network. And the miners are replicating and mining the entirety of the rest of this network. Each chain itself isn't owned by a company or someone. It's as ownerless as Bitcoin or Ethereum is. It's just that instead of there being one Ethereum chain, there's now, in this case, 20, and they're just braided together. So this braided structure really does get to the security of the system. We were going after it for throughput. We saw overall that throughput, that scalability was a really core concern, and we didn't want to go with a proof of stake approach. If we had actually gone with the proof of stake approach, we would have already launched because we already have a deterministic Byzantine fault tolerant consensus algorithm that's been running in development for a year. That's scalable BFT. I have a regulatory background, which is we're going to get into later, so I have reg issues with proof of stake, but also proof of stake fundamentally, not having a Nakamoto-style consensus means that it isn't this open, trustless, censorship-resistant thing. It just totally changes the dynamics when you remove the ability for anyone in the world to go and buy some CPU, to buy some GPUs, and go start mining on the network. So we used to Merkle trees. We call these Merkle cones. A Merkle tree is every single blockchain is just forms a Merkle tree. So every node, then you have a tree that drops down. These cones are structures that naturally come out of using graph theory with a diameter as a way to structure how blocks are related to each other. So from this block's point of view, it is directly and then indirectly referencing the entire network 3 blocks behind itself. And when it's 3 blocks deep, the entire network references it. And in this in-between region, you end up with the reference not being global. And that's a feature, it's not a bug. One of the reasons that the block stream, the every block references every other chain, or every chain references every other chain approach wasn't followed, is that it only scales to around 10, maybe 12 chains. And after that, to make any next block for the entire network, you would need to reference, let's say there's 100 chains and they all reference each other for the next block. So instead of it taking multiple steps, it's just this thing has to reference all, let's say there's 1,000 here, 100 here. That is very unlikely to do in a globally replicated distributed system. It actually just won't come to consensus. So by adding this period of time, we allow this technique of having parallel chains to scale beyond just 10 or 12 chains. Now, the last key to the puzzle in all of this is that all chains mine Kadena currency. You have separate wallets on each chain, and you can transfer any asset you want between chains. We'll start with coins. So every chain, and each one of these points represents one, is mining Kadena currency. And you can move coins from this chain to this chain without involving a third party. It's all done at the smart contract level. It's all done at the user level. Actually, let's go to this one. The idea is that you delete coins on one side, and you specify where they go, where they can be created, and who can do it. And then you say, and then on the other side, you go and you go resurrect those coins. You go and recover the receipt.
So adding a real world example, say you were running CryptoKitties on one of the chains, and that application got so popular that that chain got really heavy, and the transaction fees went up. To load balance and to offset those transaction fees, you would then open up an account on a different chain that would still be running the CryptoKitties app, but your account would be on the chain that has lower transaction fees.
Yep. So easy way to see it, a lot of this stuff is very graph in nature, or just visual in nature. So you're on one chain here. This chain has, let's say this is CryptoKitties. CryptoKitties gets launched on this chain, and it clogs this chain up. This one, its peer, And this could be one of 2 chains, or it could be one of 100 or 1,000 chains. Doesn't really matter. But let's say this one has CryptoKitties on it, and it just gets clogged up because there's so much adoption, there's so much interest that people want to really get involved with this thing. And you're like, this is cool, but I don't want to get involved with it. The problem is that your account is on here, and if you want to do any transfers in Kadena Coin, you need to pay higher fees because an app that's been deployed to this chain is getting a lot of usage, which is then driving up fees because there's a lot of congestion. So you can go and delete your coins here, and once this block where the deletion occurs is referenced by the rest of the network, you can go and recreate. So you can go and create the coins that you deleted, that you burned, on another chain. And at this point, you specify that, my public key and only my public key on this chain. So this will be, let's say I'll call this chain 2 and this is chain 1. On chain 2, can create X number of coins, to the amount of coins that I deleted. And you then go and recreate those. It's all at the user level. This doesn't involve consensus at all. You actually go and draw a Merkle proof to your deletion site. And when you're doing the recreation, the smart contract will the coin smart contract will go and validate this Merkle proof. And the main thing it validates is that it's well structured, that your deletion is here, and that the Merkle proof from this point all the way down to wherever your receipt is for the deletion is valid. And then it will also check that in consensus, this leap, this first jump off its chain to a peer chain is valid. Because the consensus protocol is like part of what it's doing is building up a trustless way of having these links be tracked. So they're all tracked at the user at the smart contract level, and that's just kind of how it works. The paper goes into much more detail, but the gist is that you can have 1,000 chains or 100 chains in parallel, and you don't need a market for coins between each one. It's the same coin that's being mined, or the same currency that's being mined on each chain, and each environment is separate. So if one gets clogged, the other ones aren't impacted. This also allows you to do interesting things like load balancing smart contracts. So CryptoKitties deploys to, let's say CryptoKitties deploys to this, actually let's use this one, to this chain, to 19, and it clogs it because people are just adopting it so quickly. That chain 19 now has like a $5 transaction fee per transaction because everyone's trying to get involved. CryptoKitties can then, the developers can then go and deploy new smart contracts, clones of it effectively, to 8, 16, and 17 that say, okay, that are basically just their own, these local versions in these sandboxes, and now people can go and interact with these, and they also go and they upgrade 19 to make it aware of these. Because the CryptoKitties authors have the governance, own the governance of the contract. So when they go and upgrade this one, they're the only people who can. And they go and say, they go and say that, okay, now instead of just living on chain 19, you have sisters that live on 17, 16, and 8. And now instead of having, let's say, 10 transactions a second, which is close to what Ethereum does on a single chain, you now have 40 transactions a second because it's running on 4 chains. And you can load balance across these. So if you really like CryptoKitties, you can take your account, which is on this congested chain, and then move it onto chain 8. And users will naturally try to figure out a good equilibrium to be at. Developers can also get involved for doing this load balancing, but it can be done purely at the user level should you choose to. So I guess the last kind of key takeaway here is that the confirmation time. So the confirmation time in this system is the depth. So the diameter of the graph, which represents how deep a block needs to be referenced by the rest of the network, is also the confirmation time. So the question becomes, how quick can we make these block times? It's an active area of research at Kadena. We're working on it with our Monte Carlo sim, hoping to have a paper out in the next couple months that goes into detail on how block time, block size, and network configuration and diameter all interplay with each other so that we can really have a good understanding of what the security is. We just know the security is very high. We've tried to do this in a closed form Nakamoto proof. The Nakamoto proof using the Poisson distribution is actually unstable at large enough sizes. This is kind of a known thing. We just ran into it though. We should have been using a different distribution. But it basically just drives to zero quite quickly. The probability of being able to do a hard fork without 51% of the network. It drives to zero pretty quickly and then just kind of bounces around between positive and negative zero, or like right above and right below zero, which is where the instability pops up. So,
So what he's saying is that we're at good test speeds, so per chain is 10 transactions per second, and we've gotten it to scale up to 100 chains.
it's so we were using Ethereum's performance metrics for the throughput on a per chain basis, and the reason for that is that it's going to be more bound by consensus than anything else. On the private chain, our private chain runs at around between 2 and 8,000 transactions per second, and this is for a simple transfer $1 from A to B in a contract that tracks just simple currency transfers. And if you take Pact and turn off the consensus and you turn off the cryptography and you just run the interpreter in a performance benchmark, it'll hit between 10 and 14,000 transactions a second. Because we started in enterprise, we knew that we needed a huge amount of performance for the private chain. And now bringing it over to the public system, we have this massive excess of performance for Pact, but it's just not going to be, we're not going to be able to get all of it on a per chain basis, just because that's not how proof of work really works. That is the end of the Kadena section. I would love for questions. Yeah. Does anyone have questions? We can have the mic brought.
Okay.
And you can ask in Korean, and we can translate it.
Yeah, I'm not good at English, but I can try it.
I'm not good at Korean, so don't worry.
Yeah, I'm trying in English. Can I add some more chains? As you described, how many chains do you describe? Yeah. For the case, can you add another chain in that configuration, or?
So it's a great question. And this is the roadmap to over this next 5 years that I had mentioned before. So you can't just add a chain onto it, but you can hard fork from, in this case, 2 to 20 chains. Graphs that work for Chainweb go up into the billions of chains. Now that's the academic theoretical limit. Not the physical, the practical. The physical practical limit is around, I'd say around 10,000 chains in a graph. And the reason for it is the bandwidth, the just internet throughput needed to globally replicate any more than 10,000 chains. The numbers get huge. So it's bounded by the amount of fiber optic cable we have, much more than it is by the protocol itself. The cool part of Chainweb is that now that we've shown that it really does work for this size, you can change the size of the graph, and it's very general over the graph that's used. So you can change from something that is optimal to something that is less optimal if you want to. You can change something bigger or something smaller, and the protocol works basically the same. There's next to no difference. So once we plan to launch at probably 50 chains in parallel, maybe 20, but probably 50. And then as adoption increases, as the users are using, let's say the utilization is 200 transactions a second on average. Then we talk about a hard fork to more chains. So we go 50 to 100. That's now 1,000 transactions a second. And then users consume that extra capacity. And then we say, okay, it's time to do another fork from 100 chains to, let's say, 500 chains. And then again and again for several years as adoption picks up. That's a complicated one. Does that answer your question? We should get this translated into Korean. Actually, yeah. Yes.
So I may not be understanding this network completely, but a quick question is the touch points of the verification process that is required in order for this operation to be processed. And another thing is how much mining it'll require. So, like for example, is there a scenario where there's a shortage of miners supporting the network, for example? So I'm just kind of curious about how much of an energy power that is required for this operation to be sustainable, or just you're assuming based upon.
It's a great question. So the first question is the validation when mining new blocks. Now, baked into the protocol, so let's say you have 3 miners, 3 mining pools, and they're racing to mine each of these blocks. There's nothing that says in the protocol that the majority of the hash rate needs to be replicating both chains. That argument is an economic one, which is that if a miner isn't replicating both, and they're only replicating one chain, then they will be unable to validate, but also unable to produce blocks on a peer chain, on somewhere else in the network, which means that they don't have the choice of load balancing their hash rate across the network. So because of that, they're more likely to get a duplicate block here. And if you have a duplicate, it's just waste because you can't use it. It's not like Ethereum with uncles where you can actually use, like if you have multiple solutions, you can actually sort of use them. It's just strictly waste. So it is economically dominant for a miner to replicate the entire network if they're a serious miner. With the reason being that, and this gets to your second question of energy use, the energy use between this 2 and this 20 chain system stays overall the same. There is some minimum bound where if we only have one CPU that is from the 1990s mining the network, then you can't make difficulty small enough for it to work. But the practical is that's kind of the theoretical bound. The practical is far above that. Of if you only have one miner with 10 machines mining the network, then you don't exist. And we don't really plan for, I don't see the point in planning for that failure mode because we don't exist at that point. So the energy use and the size of the network are more or less separate because the vast majority for a miner, their resources, the electricity used, the infrastructure invested in, all of these things, it goes into mining, into finding solutions, not into the servers that replicate, let's say, Bitcoin at this point, or Ethereum. It's a very small amount. I've had people estimate it being between 2 and 5% of the total annual cost to a miner. So from a miner's point of view, let's say you have enough energy to really be mining on this block. The added cost for you to replicate this, or for you to replicate the rest of the network, is minuscule compared to the downside of getting just regularly duplicate blocks. By only being able to mine a subset, you just decrease the expected value on the return on your investment of all this mining hardware. So you may as well at that point replicate the rest of the network. And at that point, that's when validation kicks in. Because you're replicating this, and you know that if someone puts in a bad block here, that you should still be mining on it. And so does the rest of the network. And it's the economics that drive to the solution to both of the things that you posited. As for overall energy use, that will always increase until it is economically infeasible and completely irrational, because miners aren't totally rational, but they're rational-ish, to continue to add more and more hash power. Kadena is designed with that in mind. Its token economic model has this. We haven't built the collateral for it, but it's built with the idea that the network does well, and that the reward works at kind of a sweet spot. It works on a lower amount, but especially during early adoption, miners are believers in the long-term vision of the project, versus later on when the hash rate really picks up, people are looking at it for the economic reason. And that's where it's tuned for, is that ramp up of public adoption